Hi, this is Mr. Biter, and these are the notes for Newton's three laws of motion. The key questions are, who is Sir Isaac Newton? What is inertia and Newton's first law of motion? What is Newton's second law? How do you calculate force using Newton's second law? And what is Newton's third law? It's also important to note here, it's not only important to know the three laws, but also what they mean and examples in real life that we can apply them to. Here are the words to know. Inertia, Newton's first law, Newton's second law, Newton's third law, mass, acceleration, force, Sir Isaac Newton, Newton, and Graham. Who is Sir Isaac Newton? Well, Sir Isaac Newton was a very famous scientist who discovered many things about forces, light, and math. He was given credit for inventing or discovering calculus, a branch of mathematics, as well as a lot about optics and how light is made up of all the colors. But he's probably most famous for his three laws of motion, which we're going to learn about. What is inertia in Newton's first law of motion? Well, inertia is a tendency of things to just keep moving the way they are moving or not moving. Newton's first law is also called the law of inertia. The law states that an object at rest will remain at rest and an object in motion will remain in motion with the same speed and direction until acted upon by an unbalanced force. So basically it just says that things are going to keep doing what they're doing. That's inertia, and that's Newton's first law. A famous example is when we look at seatbelts. Why do we wear seatbelts in cars? Why is it safe? Let's take a look at that example. This example is pretty silly, but it's a great demonstration of why we should be wearing seatbelts and how objects will keep doing what they're doing. If you're in a car and it's going at 45 miles an hour, everything else in the car is going at 45 miles an hour as well. And if you're not wearing a seatbelt, you will continue going on in the same speed and direction until something stops you, until there's another unbalanced force to slow you down, whether that's the pavement, a tree, a pole, the dashboard, the windshield, whatever it is, you're going to keep going the same speed and direction until something stops you. Hopefully, it's a seatbelt. Oftentimes, students tell me, that they can do, some crazy things, why they don't have to wear seatbelts. Maybe a relative that has reasons why they don't wear seatbelts. Well, think about the physics involved, the kinematics, how much the force is involved, and the speeds that are involved. Take a second to read some of these. Imagine a car with the dashboard mounted on the front bumper facing away from the car traveling down a road at 45 miles an hour. Would you be willing to stand in front of it? Of course not. But the collision is no different than crashing your own car into a stationary object at 45 miles per hour without a seatbelt fastened. Whether you hit the dash or the dash hits you, the results are the same. You're still traveling at 45 miles per hour at impact. Look at this one. A 7-story fall. 2 seconds after falling out of a 7th-story window, a person would hit the ground at a speed of 45 miles per hour. The bodily impact would be essentially the same as a 45 mile per hour unbelted crash, as mentioned above. None of us would intentionally let our children out on a high window ledge. Okay? Yet, in Colorado, where this website was made, and in New York, many of us don't buckle up, either ourselves or our kids. Why not? Okay? Some people think that by throwing their arm out, they can save someone. That's not going to happen. Right? If you have a 50-pound child in a 45-mile-an-hour crash, that'd be like trying to stop 1,000 pounds. That is ridiculous. It's not going to happen. That requires way too much energy to try to do that. We also have some other things, and take a second to read these, especially these seatbelt myths. These are the excuses that people give us for why they don't wear their seatbelts. And you've probably heard some of these before. Take a second to read these yourself. If you know of someone that has an excuse for not wearing a seatbelt, feel free to add it to the comments for these notes on Edmodo. So that's why the seatbelt is a great example of Newton's first law of motion. Everything in a car is traveling at the same speed as a car and will keep traveling in that speed and direction until an unbalanced force acts on it. So take a look at this again and see if you can answer that question on your paper now that you've heard some reasons. If you can't, go back and re-watch the last part of the video. What is Newton's second law? Newton's second law states that the net force on an object is equal to the product of its acceleration and its mass. All this means is F equals ma. Force equals mass times acceleration. Okay, if we have mass, we have acceleration, we can figure out what the force is, and vice versa. If we have mass and force, we can figure out acceleration. How much force does it take to accelerate a 5 kilogram object 50 meters per second? Just like you would for any math problem, you're going to write out the equation first, substitute in values, and then solve. Notice that when we multiply kilograms and meters per second squared together, we can then change that to newtons. And that's only the case if we have kilograms, though, and meters per second squared. Otherwise, we'd have to convert whatever these are to kilograms and meters per second squared. What is Newton's third law? Whenever one force exerts a force on a second object, the second object exerts an equal and opposite force on the first object. Another way of saying this is that for every action, there is an equal and opposite reaction. One force is called the action force and the other the reaction force. And action and reaction forces do not cancel since they're working on different objects. All right, we noticed before when we looked at net force that we had our force diagrams and they're working on the same object. So we could have, if they were the same forces, amount of force going in opposite directions, it would be balanced. That's not the case here. These are acting on different objects and they're equal and opposite. So let's look at what this is in real life. Here's a guy running off the boat onto a dock. Why is that boat moving backwards? Well, he's pushing it, right? It's going backwards. The boat is also pushing him. So he pushes on the boat with a force. The boat, the canoe here, will push in the opposite direction on him, so he's able to go forward. These are equal and opposite forces. Now imagine if that was a really big boat, like a cruise ship or something. Okay, he could easily run and jump off of it. He's still pushing on it, and it's pushing back, but it's going to accelerate less because it has more mass. So when we're looking at this, we want to think about not only the amount of force or push and pull involved, but the mass of the two objects that are interacting. Let's take a look at some other examples and make sure you have these in your notes. We have two objects in the first drawing. We have the bat and we have the ball. The bat will hit the ball, the ball will also hit the bat, equal and opposite. But if you're well planted, this will have a lot more mass in the ball, and therefore the ball will accelerate forward more than the bat will accelerate backwards. We have an action force here. The tire pushes the road. Well, the road pushes back on the tire. That's how the tire is able to move forward. Same thing if you were stepping, you push with your foot, the ground pushes back onto your foot, enabling you to walk forward. Another classic example of action and reaction forces is the rocket. The propellant, right, pushes out back, causing the rocket to move forward. This has mass. The propellant coming out the back of the rocket has mass. The rocket itself has mass, and therefore this mass and this mass, right, will also have acceleration, and the forces will be equal and opposite. Okay, so not only does the rocket push on the gas, but the gas pushes on the rocket, making it go forward. Now, this may seem kind of confusing right now, and certainly it takes some thinking to understand action and reaction forces. But just remember right now that for these, there have to be two objects, and the forces act in equal and opposite directions.